Well, welcome back, everybody. Thanks for coming back. Sorry about the little issue with the room, but it's all set up now. It's my pleasure to introduce Michel Devoret, who invented this whole field. So very happy to hear tell us about it. Michel has recently moved to UC Santa Barbara, but I think it's still maintaining a decent sized presence at Yale for the time being, and also at Google. So this would be hat number 4 or 5 that you're wearing as presenter here. We appreciate your time. So take it away.
Thank you for this information. Okay, yes. So thank you for coming to this introductory lecture. So what I will try to do, since already as I was this morning covered a lot of topics, is to give you a sense of how we can, in this field of quantum circuits, how we can have degrees of freedom that are similar to those of atoms. We are essentially synthetic atoms. And the big question is, why can they even compete? How can actually the degrees of freedom of a circuit, an electrical circuit, can compete with atoms? So this is what I hope to accomplish. I think I have too many slides and they are not even in the right order. So I apologize in advance. I think we should make this presentation as interactive as possible. So if there is something you don't understand in the slide, please interrupt. It doesn't matter if we don't go through all the material here. I think it's important that I actually answer some of the questions you may have for this field. And I want to acknowledge his colleagues, Steve Gervin, Jens Korp, who's here, Zlatko Mineyev, who spoke this morning, and you all with whom I had really great discussions. And this was very important for me to have this dialogue to understand the big picture of our field. Okay, so what I hope to achieve here is an introduction to a topic I'm going to give in the advanced track, which is the construction of an Hamiltonian from a circuit diagram. So I think the main focus of this workshop is to allow the students to design, to get an hands-on introduction to design and experiment the software. But before you experiment with this software, you have to have an idea that we can take an electrical circuit, which is represented by a circuit diagram, and then we do quantum mechanics with it. So it means that we are going to quantize the degree of freedom of the circuit.
What exactly is the degree of freedom of the circuit? How do you even construct this? So it's not something, there's really some problem.
I will fix it.
Okay. So this will be something central here in the discussion, is what are the degrees of freedom of a circuit? How do you find them? How do you, what does it mean to quantize them? So this is what I hope to accomplish in this lecture. Okay, so just as an example, what I mean by a circuit is an assembly of electrical elements here, and then the goal is to end up with an Hamiltonian like this and to do quantum mechanics. And this topic, as Zlatko has presented, is covered in a series of evolving articles, and I refer you to the last one here. And this contains essentially this what I'm going to tell you. Okay, so what does it mean to construct an Hamiltonian? Well, let's before we go to circuits, let's speak to mechanics. So we have this mechanical system, this macroscopic system, a pendulum, and I have chosen the pendulum because it is the simplest nonlinear system with only 1 degree of freedom. And there's only 1 degree of freedom, which you can take as the angle that the pendulum makes with the vertical here. And so here, there's not a big, everyone accepts this degree of freedom. We are going to see that for an electrical circuit, this is not so easy, but here everyone accepts that this is a valid degree of freedom. This is its velocity. So the route to the Hamiltonian is to write first the Lagrangian. And the Lagrangian in mechanics is very easy. It's just the difference between the kinetic and the potential energy. And in mechanics, there's no ambiguity as to what constitutes the kinetic energy. The kinetic energy is the energy associated with the velocity of the system. And so from the kinetic energy, you subtract the potential energy. And then once you have the Lagrangian, you can identify the conjugate momentum of the configuration degree of freedom, the theta. You have this p theta. And then the Hamiltonian is just essentially a combination of the Lagrangian and this product of the velocity times the conjugate momentum. And you have to express this expression here in terms of both the configuration variable theta and its conjugate momentum. And this is how you construct the Hamiltonian. And why do you bother? What is the Hamiltonian good for? Well, it's first of all a list of parts. It is where you read your variables. These are the variables of this function h. And you can distinguish the variables like theta and p theta, and you should not confuse them with parameters. This is going to be super important because in quantum mechanics, the variables like theta and p theta are matrices, but the parameters are scalars. So they are proportional to the identity matrix, and your variables like theta or p theta should never be proportional to the identity matrix. So there's a huge difference between parameters and variables in quantum mechanics, unlike in classical mechanics, where for the moment, for some time, a variable can be taken as static, or you can take a parameter and say that you vary with time. Okay. So then you can, with this formalism, it's easy to apply a time-dependent force. You just add a term to the Hamiltonian. You generate the equation of motion from it, and the equations of motion generally have one less parameter. For instance, the characteristic energy of the system will be contained in the Hamiltonian, but not necessarily in the equations of motion. And finally, most importantly, this is the usual starting point of the quantum mechanical treatment. It is by diagonalizing the Hamiltonian in the correct basis, in a well-chosen basis story, that you get access to the energy levels and all the quantum properties. Okay, so now that we have reviewed classical mechanics, how do we apply these ideas to an electrical circuit? So the best way to start is to take a simple LC oscillator. So this morning, Zlatko has amply covered this subject. This actually circuit is what you have in your cell phone. This is the coupling circuit to your antenna, and made of, if it's made of aluminum, it will be superconducting at low temperatures. And there is something really remarkable which happens is that even though you have billions of electrons and potentially as many degrees of freedom in this macroscopic system, at low temperatures, and you can essentially consider that you have only one remaining degree of freedom. And this degree of freedom, you can view it as the center of mass of the condensate of electrons. All the electrons at 10 millikelvin as condensed in a microscopic state, if you want. And the center of mass of this electron fluid is the remaining degree of freedom. And this is quite deep. And I want to spend some time explaining why this is the case and what are the potential restrictions to this idea. But it's very important that you understand that in this field, the degree of freedom is really collective. Actually, it's not so different than the pendulum that I addressed before. The pendulum, you could have taken also the center of mass of the pendulum. Let's launch into this discussion. And let's really make a side-to-side comparison between an atom, let's say the hydrogen atom, which I represent here, like classically, of course, like an electron going around the nucleus. And here in the superconducting LC oscillator, you have the capacitor plates here. And the green stuff is this electron fluid, and red lines symbolize the background of ions. The circuit is neutral, but there's exactly the same amount of charge in the metallic lattice of positive ions and the electron condensate. So let's animate this slide. So the hydrogen atom, you can think of its dynamic as the motion of the electron. Of course, the motion is quantum, not classical like this. But if we look at the equivalent for the circuit here, it will be essentially the electron fluid sloshing back and forth between the capacitor plates. And you see that it's basically just like water sloshing in a reservoir, but the fluid is completely incompressible. So this is the analogy. So in an atom, you have in the hydrogen atom, you have a unique electron, and here it's the whole superconducting condensate, which plays the role of the electron. The current to the inductor here is the analog of the velocity of the electron, and the force on the electron is if you want, the voltage across the capacitor, which is the restoring force that brings equilibrium in these capacitance. Okay, so and in fact we are still trying to answer this question here. Can a collective variable, which involves billions and billions of atoms, be as perfectly quantum as a single atom? And this year, we've reached the threshold where a transmon can have a quality factor as good as the hydrogen atom. The transmons have become so good that now they are as coherent as a hydrogen atom. Of course, there are atoms which are much more coherent than the hydrogen atom. All the atoms that are making atomic clocks have way better quality, but it's quite a threshold. I think that this field has reached at least the point where an artificial atom can be as good as a textbook atom. So the main difference between the hydrogen atom and the LC circuit that I have mentioned is that there's a very different dimension. So the hydrogen atom is a tenth of a nanometer, but our transmons nowadays are millimeter across. So it's many orders of magnitude, which has both a lot of merit and a lot of disadvantage. So the merit is that this is so big that it's very easy to couple to. You can just actually put wire on this atom and couple it to another artificial atom. This is much harder to do with the natural atoms. They are only weakly coupled to each other. Of course, the problem is that this dipole moment here is so big that, of course, this atom will couple to anything else. So you have to be very careful when you design the circuit to avoid spurious couplings, because otherwise the coherence of this object will fall down very rapidly. So now let's discuss the question. So when you write the Hamiltonian of the hydrogen atom, we can do this just by treating it as a mechanical system. We take the potential energy of the electron, we take its kinetic energy. This Hamiltonian can be written essentially very naturally. The problem here that we want to solve in this workshop is, what do you do here? So how do you take this very collective system and reduce it to a simple Hamiltonian like an atom? What are the approximations? How good is this pathway here? So this is what you have to, I think, this is what you have to learn. It's not so much the end result, but how we go from here to there. What are all the pile of approximations? When are some approximations really excellent and when they are actually terrible? This is, in fact, I think this workshop is very good because it discusses all these points. Okay, so what I want to do now is to try to give you some elements on this question of reducing the number of degrees of freedom from the Avogadro number to essentially 1. How we start from a near Avogadro number of degree of freedom and end up what are all the conditions? Well, let's start with by learning what degrees of freedom you have in a metal. So at low temperature, you can take the positive ionic background, all the nuclei, they form an ionic background, and you can, in a first approximation, forget about all the degrees of freedom of this system. They are phonons, of course, but they are essentially frozen at 10 millikelvin. But inside, floating inside this positive ionic background, you have the electrons, which form a liquid. And the combination of the two, this model is called usually the Gelion, because we are not going to go into the detail of where are the positive ions. Now, what are the degrees of freedom of the electrons? Well, the electrons form, so this is a giant molecule, if you want, with many electrons, but thanks to the Fermi principle, the electrons pile up in all the levels here up to the Fermi energy. And the problem in a metal is that the distance between energy level, even in a very small electrode, it will be extremely tiny energy. It's 0.1 nano electron volt. It's the distance between energy levels here in the metal is much less than the temperature. So a normal metal actually is not going to behave as a single atom because you can excite very easily what is called electron hole pairs. You can promote an electron deep in the Fermi sea and then put it up. And that can be an energy comparable to a thermal excitation. So this is what we call heat. In a metal, it's these excitations known as electron hole pairs. Fortunately, when a metal is superconducting, you have a gap. So you cannot excite electrons here below very easily because you are fighting this gap here, which is about Kelvin in aluminum. So if you had, theoretically, if you have an aluminum ball the size of the Earth, at 10 millikelvin, there would not, in thermal equilibrium, there would not be one single broken Cooper pair. You would have the energy, the thermal mass would not be sufficient to excite any electron. Of course, there are some problems because you can have cosmic rays. You have all kinds of adverse phenomena like that that tend to still excite electrons, break, or another way to say it is that you can break Cooper pairs. But the record now is that we can get the fraction of excited Cooper pair down to 10 minus 10. So this is pretty good. So there are methods by which we can really suppress these excitations to a very large degree. So that's one aspect. Superconductivity and low enough temperature and protection from all kinds of perturbing influences, good shielding. So that's an obvious ingredient. But then there is something else because actually a piece of metal, all these electrons can have collective motion. So, for instance, if you take a thin film of metal, you can actually excite the bulk. There's a bulk excitation of the electrons. You can displace all the electrons, let's say, collectively from left to right. So a charge plus Q will appear on this side of the film, and you will have a minus Q on the other side. Fortunately, and this is where the charge of the electron enters, this mode is very high frequency. So this mode happens at the plasma frequency here, which is actually proportional to the density of carriers. And this is so high, and the mass of the electron is so small that this frequency ends up being actually, for aluminum, it's in the UV.
Michel, I have a question about the previous slide.
Yes.
So first, in this picture on the right, you show like all electrons are still form some kind of hierarchy of levels. Well, if they're all in Cooper pairs, I would imagine they just all being like at the same ground state level, which is macroscopically populated.
No. That's not. I think you are alluding to the fact that somehow one could see superconductivity as a sort of Bose-Einstein condensation, but that's really not true at all. So, so aluminum is a BCS, a very good BCS superconductor, and this notion that electrons pair and then they both condensate doesn't apply at all in to aluminum. That's the wrong part to understand superconductivity in aluminum. It's true that in atomic physics you can actually both condensate atoms, and but they form something which is quite different than the electron condensate. If you want, there is the electron interact in a way as to open a gap at the Fermi level. We will. It's a special gap. I agree that you should not, for instance, confuse this gap with the gap in a semiconductor, but don't think of this middle energy as a sort of energy where Cooper pairs would lie. Some people talk about in this way, but this is very misleading in my opinion. No, you really have some states exactly. In fact, these states are exactly the same state as in the normal metal. If you look at the wave function of these states, they will be exactly the same as in the normal. What changes is the way they are populated. Or if you want, what distinguishes a superconducting metal from a normal metal is this opening of the gap and the fact that you can never have a single usually these levels occur in pair with electron up and electron down. And in the normal state, you can have states that are filled with only one electron. But in a superconductor, a state can be filled only with 2 electrons or 0 electrons. Okay.
And you also said that there is no spontaneous excitation because there's, the Boltzmann suppression factor is really small.
Yes.
But there is also like a macroscopic number of states next to the lower side of the gap. If you like take the product of the two, what if one?
No, you're right. So we are exactly now dealing with this question. I have covered this electron hole pair excitation. Now we are looking at another excitation where all the electrons shift bodily. So that indeed is not contained.
I don't think this is what I meant. Like for any single state, there is a low, like if you put one Cooper there, it has a vanishing probability to to get like to an excited state, but you have macroscopic number of states.
No.
Okay.
The problem with superconductivity is that a lot of people feel authorized to say things in popular journals which are completely incorrect, it's a subject in which there's a lot of confusion. And in fact, it would be you have to allow me to speak this subject because I could fill two lectures simply debunking all the misconceptions of superconductivity. So we will skip this, but thank you for your question. It's an enormous subject. I would have a lot to say, but
we can discuss.
So I prefer, let's say, why not like finish and then we'll cover other aspects of superconductivity if you want. But what I want to say is that in a superconductor, besides this breaking of Cooper pair, which is essentially corresponds to taking electrons below the gap and bringing them above, there is also what are called plasmon excitations, where all the electrons are shifted bodily. But thanks to the Coulomb energy, this type of excitations costs you a lot. At least when you take this film and you displace this electron like this, you can compute that the energy is very, very large. So for instance, if you would first displace this plasmon, then they would oscillate back and forth, and the energy associated with this is extremely high. So this is very important because without this Coulomb interaction, we could have eventually very low energies here. And in fact, this is what we are exploiting. We are taking this plasmon excitation, and then we are going to progressively lower their energy. So instead of an excitation of a thin film, I am changing the ratio of the piece of metal. So instead of taking a slab like this and moving the electrons across the slab, I take a long rod like this, and then moving also the electrons from left to right. But now I have some plus charge at the end and some minus charge at the end. And now if I redo the same calculation as before, in the limit where the length here is much larger than the width here, I have what is called the surface placement. Surface is not a very good term because the excitation is still inside the metal. But now the frequency is much smaller. So we went from basically the UV regime to something that is fixed by the speed of light. So you see, we take the speed of light and then we divide by something proportional to the length here, and we get a frequency. And that's for 100 micro long wire, that's something like 100 gigahertz. So we've went from UV to, basically millimeter wave, but we can go even further when we continue to change the shape of this rod. We can take this rod and put it and bend it and make an annulus, and then we can leave a very small gap here in the annulus, and that will create the equivalent of an inductance here and the capacitance. We can make the capacitance actually as large as we want if we make the gap smaller and smaller. And you see now I can apply another formula to compute the frequency. I can say, well, this is an LC oscillator, and the frequency is given by this formula. And then when I compute typical values here, I get values that are similar to those quoted by Zlatko, and I get a few gigahertz. And that's basically what we exploit. So the degree of freedom is this collective motion, this bodily motion of all the electrons. And by moving bodily in the wire, some charge appears here on the capacitor. So this is how we arrive at this unique degree of freedom. So if we don't excite Cooper pairs, this should be a very clean system. The limitation is the insulator here. If this would be a freely standing in vacuum, then this motion doesn't excite anything other than the electrons, and this could be extremely good. Unfortunately, we have to fabricate this on a substrate, and on a substrate, the electric field here that develops will couple to impurities in the substrate to this infamous two-level system. So we have to work with chemists and material scientists to remove as much as possible the impurities from our substrate. But as far as the physics is concerned, in fact, this is a pretty clean system. And this is something that I find remarkable. So now that I have explained how we can have something rather pure, let's look at this transition. So we have this physical distributed system, and we represent it by just circuit elements. And I have explained, how good this can be. So once you have these different circuit elements, you can go to the Hamiltonian, and then I'm going to give an introduction here on how this is done. So you begin by the classical Hamiltonian, and then you go we have to discuss this trick. So you take this classical Hamiltonian, and then all you need to do, apparently, is just to put a hat on the symbols. But this actually is more complicated than it sounds, because well, these symbols with the hats are operators, and the operators do not commute. So this comes first. So don't let people tell you that going to quantum mechanics is simply putting hats on the symbol. What you first need to know is the commutation relation between your various variables. And this is where there's a lot of discussion. Where is this coming from, actually? And is this always true? And what exactly is the phi and the q here? How can you define this correctly? Where all this comes from? So this is what I would like to discuss, now. Again, I will not stress this enough, but quantum mechanically, there's a huge difference between the variables, which are what the Hamiltonian depends on, and the parameters. Which is your mission is to really distinguish between the two. Also, I want to point out that just putting the hats on the classical Hamiltonian doesn't always work, because there's some ambiguity. Let's suppose you have something like this here in your Hamiltonian. It's not usual, but it could exist. Then, well, there are different ways of putting hats, you see. So you really have to know what you're doing when you go from classical variables to quantum variables. One good guide is mechanical analogy. After all, an LC circuit is the equivalent of a mass spring system, so we can get some inspiration from analogies. But at some point, some really sophisticated methods will be needed. So how come we declare that we have, so in this LC circuit, we have these two variables. You have the flux through inductance here, and then the charge and the capacitance here, and we declare that phi and q are exactly like position and momentum in mechanics. Well, okay, so I think Zlatko has covered this in detail this morning. Let me just mention something that I think he did not mention, which is really funny. So if you look at the wave function that he described in great detail of this harmonic oscillator, let's take the first wave function in the excited state here. You see that it has amplitude both for positive and negative phi. But what does it mean? It means that in one part of the wave function, the current flows this way around the clockwise, and the other part of the wave function, the current flows in the other direction. So you have really a strange superposition of state here. In one state, all the electrons flow in, let's say, clockwise, and in the other state, they flow in the opposite direction. So this is a bit mind-boggling. Something else that I would like to mention is that if we had some dissipation in the form of, let's say, a resistive element, after all, I mentioned that the circuit has to sit on a substrate, and the substrate could have introduce some dissipation. Well, then the levels here are no longer sharp. They become wide because of this relaxation, and in fact, the higher, the broader. In a good approximation, the width of the level is essentially proportional to the photon number, the excitation number, and inversely proportional to the quality factor. So we need to make these circuits with as little dissipation as possible. But as you will see, actually, removing all dissipation would be very bad. We need dissipation. We just need the right form of dissipation because you need to start from a well-defined state. For instance, you want to start from the ground state, and the way to reach the ground state is by dissipation. It is dissipation that will force the system to be in the ground state. You need cold dissipation and the right one. Okay, so coupling. So let's. There was one question this morning, which was we cannot use an harmonic oscillator because if we try to leave the ground state and go to the first excited state, like shining microwave, in fact, you populate all the states because of this degeneracy in transition energy. So we cannot use a linear system. We need a system that is not a parabola, but something else. It could be any shape of potential, but for instance, this one which flares up at the top will do because what is called negative anharmonicity. As you climb up the ladder, the transition frequency becomes smaller and smaller. And if you look at this transition frequency, for instance, at high temperature, you would have an emission spectrum. You would see different lines here. So this is the advantage of a nonlinear system, is that you can shine a light at these various frequency and separate these various transition. And so this means that your atom is controllable. That's very important. But it's not enough. It's not enough to have this difference in transition frequency. You need the dissipation to also be small enough, because what counts in the end is the separation between two transitions and their width. This is very important. So the question is to have enough nonlinearity, compared to it's the ratio of nonlinearity to dissipation, which counts in the end. So you can either have something which is weakly nonlinear but extremely non-dissipative, or choose a system which would have much more nonlinearity at the expense of more dissipation. The performance could be the same in the end, but in the second solution, your system will be much faster. And that could be an advantage. So don't look just for the nonlinearity or for the dissipation. It's the ratio that counts. Okay, and okay, so we need another element. Now let me discuss something extremely important. It's this phenomenon of Josephson tunnel. So when you have a tunnel junction, which is a sandwich of two superconductors with a very thin oxide. So by the way, we represent this component by two symbols, because there's the tunnel of electron, the tunneling of Cooper pairs, which is represented by this symbol, but we also have an ordinary parallel place capacitance here across. So when you have such an element, there's actually two processes that you should distinguish. So I am representing the levels on both sides and the fact that there's a gap here. So you can have what is called incoherent tunneling. So you can have, for instance, you can have an electron, a unique electron going across the barrier here, and that creates an electron hole pair, but it's a strange type of electron hole pair, because instead of the electron and the hole being on the same metal, here the hole is on one side and the electron is in the other side. And this process is incoherent. Why is it incoherent? Well, it's because the density here of level is extremely high, And when this happens, in fact, you have a continuum of states here. In my drawing, where there's a separation between every level, it doesn't look like so, but in practice, because these levels form a continuum, this process is essentially governed by Fermi's golden rule. So it is not reversible. It decoheres extremely. The decoherence time for such a process is much less than a nanosecond. So, but this was the discovery of Josephson, actually, for which he got the Nobel Prize. There's a process which is coherent, in which two electrons actually go from one electrode to the other. And so the degree of freedom here that is involved is a change of Fermi energy. You see here the gaps are aligned, the gaps are in front of each other, but the gap in a superconductor, unlike the gap in a semiconductor, is a mobile gap. So you can take this gap and move it up and down. This happens, for instance, when you take charge out of the superconductor. So when you take charge out of a superconductor, you have to lower this gap. It's a bit like, it's like a boy on the sea here. And so this is what has happened here. With you can actually create this Josephson tunneling by just removing electrons here, changing the gap on the left. You lower it on the left, and you make it a little bit higher on the right. And that's called Josephson tunneling. And the great discovery of Josephson was that everyone thought that this process would eventually exist, but it would be extremely weak and totally actually negligible compared with this one. But in fact, because you have many ways to take two electrons from the left and put them on the right, and this process is so degenerate that the smallness of each sub-process is actually multiplied by the number, and in fact you get quite a large matrix element in the end. So what I want to stress is that this process is irreversible, it's incoherent, but this is perfectly coherent. This happens with no entropy production. There's absolutely no entropy involved in this, and this is governed by a matrix element, and this matrix element is called J here. And this is an explanation of why you have cosine. It was there was a question this morning on the cos phi. Well, the cos phi is very fundamental because cos phi is actually the sum of these two complex exponentials, and each complex exponential corresponds to a shift by 1 Cooper pair in one direction. So this transfers 1 Cooper pair from left to right, and the other term from right to left. By the way, here in my nomenclature, this big N doesn't represent any photon number. It represents actually the Cooper pair number. So this big N is the number of Cooper pairs that have gone from left to right. Okay, well, then we can go from this potential to this current phase relationship. So this is what Zlatko has also covered, the fact that the current across a tunnel junction is an oscillating function of this phi here. By the way, this phi is a strange variable. It's obtained by integrating the voltage here. So it's a primitive of the voltage across the tunnel barrier, and it's a strange variable because it has nothing to do with the magnetism. It is not associated with a magnetic field. it just represents the acceleration of electrons across the insulator, which is so this is called kinetic inductance, and there are two forms of inductance. There's an inductance which is due to the fact that you establish a magnetic field across around the wire, and that costs you energy. But there's also an inductance associated with the acceleration of electrons, which have finite mass, and that is also appears as a kinetic energy. Okay, so if we integrate the current and we get the potential, then we have this potential, and then we have energy levels. So then let's see, how much time do I have?
Well, we started a little bit late, so maybe 5 minutes.
Okay, so maybe very rapidly, I will just flesh out this question of circuit quantization. So we have these three types of elements. We have these capacitance, and we have two types of inductances here. We have the magnetic inductances and the kinetic inductances. And each component can be represented by an energy. So instead of basically the capacitance or inductance, we can talk about energies. So this is just a rescaling. And sometimes I'm asked this question, well, these elements are only dipole elements. They have only two wires. In principle, there are elements with more wires. So these are called dipoles, but we could have quadrupoles. For instance, a transformer is a quadrupole. So how do we deal with transformers? There is this trick. You can always take a transformer and represent it by inside the transformer. You can actually decompose it in inductances by this kind of strip here of a shared inductance. Now, this is amusing because when you do this transformation, you end up for certain values of n, when you have an n which is exactly equal to the square root of the geometric inductance, geometric mean of L1 and L2, you end up with some negative values here in this circuit, but it doesn't seem to be leading to anything bad. So this is just in passing. There's also something that you can model very easily, are transmission lines, which are just LNCs. And this is very nice because you can use transmission lines to model resistances. So if you need to model a resistance, you can do it by a very long chain of LNCs. Maybe I'm going to finish by saying something about ground and circuit. So something that I tend to, so this is my pet peeve, and I take this opportunity to discuss it here. As we call circuits are circuits. What does it mean? Well, it means that the charge has always to return. So for instance, if I have a current here in this capacitance, it has to return somewhere. So you should always draw a circuit by closing all your loops. So I will impose even a more stringent law. If you take two nodes in your circuit, then they should be connected by two paths. There shouldn't never be only one path between two nodes. You should have always two independent paths between two nodes. Otherwise, the grammar of your circuit is not correct. And this comes for those of you who are maybe theorists. This is coming from the fact that electromagnetism is a gauge theory. So this is super important. So it means that this is an invalid circuit diagram. It violates local charge conservation. So I have a method for drawing a circuit. So you can draw the loops first and then put the elements on top. If they have some white in them, this will be easy. So this is how you build the circuit. And this way you're sure to never make any mistake. Now, sometimes you will see this. So what does it mean? So it means that this node is actually the same as this node. This is the symbol for galvanic ground. Galvanic ground means that you have a piece of metal actually in between these two nodes, but you've chosen not to draw it because maybe it was too long and you were lazy. So you put a symbol like this. Now, this galvanic ground should be distinguished from what is called the RF ground, which usually is drawn by a rectangle. By the way, I say usually because many authors have completely different conventions. So I am using what I think is the dominant convention, but there are variations. So there are three grounds. So what does this galvanic ground mean? It means that you have a physical piece of metal that the electrons can flow at DC. So that's called the galvanic ground. The RF ground is much less choosy in the sense that you don't need actually a metallic continuity. You could have a very large capacitance between two of these symbols as long as the microwave attenuation is less than 0.1 dB. That's considered okay. So you see, this is some kind of connection, but not as strict as this one. By the way, you should never think that the RF ground imposes the same potential. So at RF, there is no such thing as a potential. There's only an integral of the electric fields, and you should never think that the RF, a piece of metal, is at a certain potential. This just means that there is a connection between symbols of this sort. And then you have this third symbol, which you should not confuse with the other two. This is called the electrical safety ground. This is the ground that you should connect your washing machine to. In case there's a short circuit in your washing machine, you won't be electrocuted. And so this is required by the code building. So they're quite different. Okay. Well, I think I would launch this, but I think I should stop here. I think this is enough. In the next lecture, in the advanced track, I will go from there and describe how we quantize, how we take a circuit and form the electron.
Michel, there was a question from the audience, from the online people. Yes. You said that having a gap is very important to make this. Would that mean that you can't make a transmon out of a nodal superconductor? Yes, correct. Yes, you cannot make absolutely. You cannot make a transmon out of a nodal superconductor. So ITC is excluded. But you could. It depends. There are ITC phases that have been hypothesized. For instance, T plus ID that would have a gap. So. But you should not have a nodal line. You should not have states in the gap. Yes, so this is very, very important. So even when you don't have a gap, you can have superconductivity. You can pass current at DC in a superconductor without a gap. But when you try to pass a current at RF, in a superconductor without a gap, then you have dissipation. So it's only the gap is not necessary for having a current with zero frequency. That's allowed. But as soon as you have a finite frequency, then you need a gap which is essentially larger
than your frequency.